Okay, chapter 5 is on two sample tests, and we're going to be in two parts. Part A is on Bernoulli two sample tests, and then part B will be on Gaussian two sample tests. So Bernoulli means coin flips, so suppose we have two sets of coin flips. So the model for that could be the first set is y's that are Bernoulli with parameter theta y, and the second set are x's with their own parameter theta x. Both of them are IID, and notice that we don't need to have the same number of coin flips from the two populations. So we've got ny for population y and nx for population x. And the thing that we want to know is if they came from the same coin. Which is that theta y is equal to theta x. So our null hypothesis could be that they are the same. Let's write y first. And the alternative could be that they're not. As usual, we go about testing by assuming that the null hypothesis is true. So if the null hypothesis is true, which means that theta y is equal to theta x, and we could just call that theta by itself, then the MLE, using all of the data, theta hat, which we could call the pooled estimate of theta, you would get that by adding up all the y flips and all of the x flips, and then divide by the total number of flips y and x. And a compact way to write that would be sy plus sx over ny plus nx, where the sy's are just the sums of the y's and the sx is the sum of the x's. Okay, so that's a good estimate of the parameter, and therefore also makes a decent test statistic, or at least the basis of a decent test statistic. In fact, an even better one would be the difference. So we could take an estimate of theta from just the y's and an estimate of theta from just the x's. So right, this is sy over ny, and this is sx over nx. And we could call that theta delta, because that gets at a contrast between the two. And if the null hypothesis is true, then the true theta delta is 0. So how could we go about performing the test? We could do a simulation from two different Bernoulli populations with the same theta. And a good value of theta to use is what we would get if we pooled them together, because under the null hypothesis they have the same parameter. And then see what theta hat y's and theta hat x's we calculate, take their difference, and study their distribution compared to a value actually observed from a sample. So let's do that. Switching over to R here, I've got our coin flips from chapter 1, which I'm calling Y, and I'm just going to count how many heads there are and how many coin flips total. So we've looked at these numbers before, but it doesn't hurt to show them again. So I've got, I've got 18 heads out of 30. And then suppose I had a second set of coin flips, and I'm just going to skip right to the count of the number of heads. So I had 19 heads in 53 coin flips. So that summarizes our two populations. And if I wanted to calculate a pooled MLE from that, I'll call it theta hat. I like to call that THAT, or that for theta hat. So theta hat pool is just going to be SY plus SX divided by NY plus NX. Okay, so that's that value. And then my theta hat delta, I don't know why I can't see what's on here, but that's okay. Is going to be SY over NY minus SX over NX. Okay. And if the null hypothesis is true, that number should be close to 0. And it is closer to 0, but we need to understand the sampling distribution of that quantity under the null hypothesis in order to make that determination and decide whether to accept or reject the null hypothesis. So let's do a simulation. Okay. Usual for loop. All right, so I'm going to flip two sets of coins. From chapter 1, I could flip NY sets of coins with a theta value. I'm going to use the pooled one, but within reason, it doesn't really matter what you use. And then I'm going to sum up those numbers of heads, and that is going to give me SY values from the population. And then I'm going to do the same thing for X's, but I'm going to do NX of them. And then I'm going to take their difference. And that is going to be my theta hat deltas that I save. And I better make some space for that. So okay, so see how I have two copies of the simulation from chapter 1, one for the Y's and one for the X's. Really the only thing that affects these results from one experiment to the next is the choice of NY and NX, which is coming from the data. And then I'm calculating their theta hats and taking their difference and saving them. So let's run that simulation. That was really fast. And then we can do the visual. Okay, so histogram of these theta hats, which I need to show you. So there is the histogram. And then I need to put on that the observed value, V equals theta hat delta. Okay, so there is the observed value, which is in the tail. So it's going to be a close call. If I do a two-sided p-value, I'm going to do 2 times the mean of THATDS bigger than or equal to THAT delta. I did call it delta up above, yes. That's my p-value, which is 3.5%, so I would reject the null hypothesis at the 5% level because the p-value is less than 0.05. So I've determined that it's rare that I would see a theta hat delta like this if the null hypothesis is true. I should get ones that are closer to 0. So I've decided that population X and population Y used different coins because they have different theta Y and theta X values. So that's by simulation. Hopefully this is starting to seem straightforward. How do you do it the math way? Okay, so back over here, in chapter 4, we learned about the central limit theorem and the asymptotic distribution of the MLE, right? So remember, theta hats from a Bernoulli experiment had a Gaussian distribution with a mean of theta and a variance of theta times 1 minus theta over n as n goes to infinity. And that we could derive using the central limit theorem or using the asymptotic distribution of the MLE, because they both land you in the same place. So let's say we do that for theta y. So I'm just replacing these thetas for theta y and the n for ny and ny. And then we'll also do it for theta x. Okay, so I really just got two copies of the same result. Now, a familiar trick, we've done this before, so we're using that sums of Gaussian are Gaussian. We can look at the difference in theta hat y and theta hat x, which we called theta hat delta, and use that will also have a normal distribution with a mean of the difference and a variance that is a combination of the two variances. So theta y 1 minus theta y over ny plus theta x 1 minus theta x over nx. Again, this is as ny and nx go to infinity. Now, under the null hypothesis, theta y is equal to theta x, so we can simplify this a lot. So theta hat delta is a Gaussian with a mean of 0, because that theta y minus theta x there is 0. And then these are all just copies of theta. So I've got theta 1 minus theta over 1 over n, I'm sorry, not over, I make that mistake a lot, times 1 over ny plus 1 over nx. Right, so I'm just copying this down with theta being the same thing as theta y and theta x under the null hypothesis. And again, remember what we did in chapter 4. We used the weak law of large numbers to replace theta with an estimate, and the sensible estimate to use is theta hat pool. Again, you have some freedom about what estimate you use, as long as asymptotically it takes you to the right theta value, which theta hat pool will. So that gets us a standard error that we can calculate. So we can do the estimate, which is theta hat delta, which I'll now write out as theta hat y minus theta hat x. And then there'd be a minus 0 here, but we don't usually write minus zeros because that's what we get from the null hypothesis, divided by the square root of theta hat pool times 1 minus theta hat pool times 1 minus 1 over ny plus 1 over nx. All of this is in the square root. and that will have a standard normal distribution. Again, as nx and ny go to infinity. So it's an asymptotic result. Okay, so now we can go back over to R and do it the math way. So I like to start by calculating the standard error. So the standard error is the square root of theta hat pool times 1 minus theta hat pool times 1 over ny plus 1 over nx. And then my z statistic is the difference between theta hat x and y, which I already calculated as theta hat delta, divided by the standard error. And then I can get a p-value as 2 times p norm minus ABS z, the same way we get a z statistic p-value. And you can see that our asymptotically approximated p-value mathematically gives a very similar result to what we calculated by simulation. So that's part A of chapter 5.